Hello, students. Because we're on break indefinitely and we may be moving to online instruction for the rest of the semester, it's even more important that you be reading the book. I mean, whether this was happening or not, you should be spending several hours a week reading the book. But because we don't have the luxury of meeting in person and spending, 6 hours a week going over lecture material, these videos will probably focus on problem solving. So the presentation of the material, go to the book for that. I'll be supplementing that to some extent, but I think my priority here in these videos will be problem solving. So let's start with this classic problem that you'll find in any of these physics books called the Atwood machine. The first time I heard the phrase Atwood machine, I was interested. I thought it would be something involving gears and pumps and like steam coming out and conveyor belts and then like a cool little product that plops out the other end, but it's nowhere near that exciting. It's simply a pulley with two masses hanging on either side. And for now, we're going to regard this pulley as massless. Massless and frictionless. Later, we can relax those restrictions. Frictionless, massless pulley. You know, it's a wheel with a groove around the circumference and the string sits in that groove. Okay, let's suppose that this second mass starts out on the floor. I'll call this mass A and mass B. Usually I will use letters to distinguish masses, and I'll use numbers to denote different times, T1, T2, etc. That's the notation I'll usually stick with. Of course, this is mounted on something so it doesn't fall from the air, but I'm not going to try to draw that. And the result that we're working towards here doesn't depend on this assumption, but just to help you visualize this, let's pretend that mass A is greater than mass B. And if there really were no friction, if this thing's free to turn and this thing's heavier, we know that this one's going to begin to fall and this one will begin to rise. And what we're interested in is the acceleration. Now, you may be thinking, will it necessarily accelerate? What if it just starts to move down at constant speed? Well, as with everything else in this class, Newton's second law will tell you what it's going to do. This entire semester, really, that's no exaggeration. The entire semester is just F equals ma applied to different problems. If you can write that equation down correctly, then the rest of it becomes a math problem. Okay. F equals ma. We have to figure out what the m is. Well, in this problem, we've got two separate masses. So theoretically, I guess we could apply F equals ma 4 times. We could write F equals ma along the x-axis for mass A and the y-axis for mass A. That's 2 equations. And same thing for mass B for a total of 4 equations. But maybe you can see here that there's nothing interesting going on in the x direction for mass A. The only forces I can see would be the tension applied to mass A, and then of course the weight, the gravity force on mass A. So let's just apply F equals ma along the vertical axis for both masses. And there's 2 different ways I'm familiar with for setting up this problem, at least for this class 3A. Let's start by using the same coordinate system for both masses. Later, we're going to do something slightly different, but for now, let's consider up the positive y-axis for both both masses. And I will write F equals ma for both masses. That's 2 equations that we'll have. And we're going to see that those 2 equations will have 2 unknowns. Arguably 3. So let's talk about that first. Since there are 2 masses, you may be thinking that we've got 2 different accelerations to worry about. What if this one starts to fall downward and pick up speed at 1 meter per second every second? In which case the acceleration would be -1 meters per second per second per second. And then you might be thinking, well, if this thing's lighter, maybe it gets, yanked up into the air faster. So it picks up speed at 2 meters per second per second. However, we're going to pretend that this string cannot stretch, that the length of the string is always the same. And that means, imagine folding this out so that the string was horizontal If the distance between the masses is always the same, then they always have to move together, which means their velocity is shared and their acceleration would then also be shared. So this is your first example of a so-called acceleration constraint. But let's recognize that if mass A has a negative acceleration, in other words, if it's speeding up on the way down, mass B would be speeding up on the way up, which means its acceleration would be positive. So I will state the acceleration constraint as such. The acceleration of mass B, and really I should use subscripts here, the acceleration of mass B in the y direction is the negative of the acceleration of mass A in the y direction. Now, that's a lot of subscripts. This is a little pesky. Why don't we just do this? I'll say that's defined as, that's the equal sign with the 3 bars, negative A. Or in other words, the acceleration of mass A in the y direction. I'm just calling that A. That way we have a single letter to describe the acceleration of both of these masses. And really, this is one equation that we've already written relating the quantities in this problem. We've got arguably 3 unknown quantities. We don't know the tension. Remember, we're going to assume that the tension is the same throughout the string because the string is supposed to be massless. Maybe I should add that here. Massless string. As soon as you say something is massless, you've got to also agree that the net force on it is 0. Otherwise, it would have this crazy acceleration. Massless string. So the 3 unknowns would be the single tension and then the 2 accelerations. If you've got 3 unknowns, you're going to need 3 equations minimum to find those 3 unknowns. Well, we've already written one of those equations. So the acceleration constraint often is one place you can go to get an equation. Where do we go for the rest of it? Like I said, Newton's second law. So here's the way I like to do it. I just write MA with a colon, and that way it's clear that my free body diagram refers to mass A. Now, I've got a tension pulling up and gravity pulling down. I'm making a conscious choice to make the gravity force longer than the tension. Why am I doing that? Because I know, or I expect mass A to accelerate downwards. Whichever direction the acceleration points, that's the direction of the net force on that mass. The net force, you can see here, would point down. So I will say F sub y equals mass A times acceleration of mass A in the y direction. This is F equals ma, written specifically for mass A along the y-axis. Remember, usually you're applying this law along a particular axis. And now I'm going to recognize, since I'm calling up positive, the y component of the tension force is positive and the y component of the gravity force is negative. So I'll say T minus mg equals mass A times, and here's where I will use the symbol that we already decided on for the acceleration of mass A. I'll just call that A. Now, you should pause for a moment and ask yourself, what kind of a number do you expect A to be? Is it a positive number or a negative number? And because of my choice here, because A is the acceleration of mass A, I actually expect it to be a negative number. Okay, I'm going to label this equation 1. Notice it's got 1, 2 unknowns. I probably should have stated that I'm supposing the masses are given. MA and MB are given. Find the acceleration of each. All right, the y acceleration of mass is A and B. Okay, so this one equation that I've written has 2 unknowns. I cannot solve this single equation for those 2 unknowns. I will have to write a second equation. And I can get that by looking at Newton's dynamics applied to mass B. This free body diagram is equally simple. This time I'm going to make the tension longer than the gravity force because I expect this mass to have a net force upwards. Now, technically, I should have drawn this arrow for T the same length as this arrow for T because I'm assuming that the tension is the same throughout, but you'll have to forgive me for that. Sum of the forces in the y direction this time is mass b times the acceleration of mass b. Because of my choice of coordinate system, I'm still going to call up the positive direction. This time, actually, it comes out the same. The tension gets the plus sign. And here's where you must be careful. What is the acceleration of mass b? You've already decided to call that negative a. So it's m times negative a. I'll put the minus sign out front. Don't forget that we're expecting this number a to come out as a negative number. Negative would actually give a positive acceleration for mass b. That's what we expect. I will call this equation 2. And now you should observe that we have 2 equations with the same 2 unknowns. We don't know t, we don't know a. Those are the 2 unknowns in both equations. We should be able to solve those 2 equations. And you can do that however you want. Depending on your algebra education, you might recognize, well, I could solve this for t. I'd substitute in here, use the method of substitution to eliminate t. You could use linear combination, which will be my method of choice. You could even use an augmented matrix and solve it that way if you've taken linear algebra. You could use Cramer's rule. There's a whole bunch of things, a bunch of methods that are all equivalent. But here's the way I will do it. If we multiply this whole equation by -1, that would turn my t into a negative t. So take this equation, which has already been multiplied by -1, and add it to this equation, and you would have a t plus a negative t. The t's would cancel. So down here I will say equation 1 plus -1 times equation 2. And you might be thinking, well, why not just write equation 1 minus equation 2? That's fine, that would work too, but it's when you talk about linear combination, usually you're thinking in terms of adding equations together, and some of the equations may have been multiplied by a coefficient, which can be a positive or negative number. Okay. I guess rather than skip that step, I'll write it all out. So the left side of equation 1 is t minus mag, and then plus -1, I'll put minus, and then in parentheses, I'll put the entire left side of equation 2. Okay, now for the right sides. I'll add the right sides together. Plus, I guess I should write minus negative MBA. And now we simplify. Again, the whole point here was that the t's cancel. Can I factor anything out here? Do you notice that I could factor out a g here? We've got a minus, which would make it positive for the mass b term. So MB minus MA times g. I've factored out the g on the left side. On the right side, we can factor out an a. Again, minus is positive. I will write this as MA plus MB times a. And we're practically done, because what the problem was asking us for is the accelerations. Both of these could be expressed in terms of this single value, a. And now I can solve this equation for a. You can see that it only depends on the masses, and it's gonna be some coefficient times the free fall acceleration. So I will go to the next page. If you divide both sides by this term in parentheses, you'll wind up with this formula for the acceleration of this Atwood machine. The acceleration would be, I get difference over sum, difference in the masses over the sum of the masses times g, which is a very simple formula. You might even memorize it, or at least the basic content. It's just difference over sum. Now let's check here. If we compare this to the original picture, remember, I was using the letter A as the acceleration for mass A. And if mass A is heavier, we expect it to accelerate downwards. That means the letter A represents a negative number. Does this give us a negative number? Well, if mass B is in fact less than mass A, this numerator would be a negative number. So you really have to be careful with your minus signs and interpreting that. if you goof a minus sign on a problem, you could easily get derailed and end up with the wrong number. Now, there's another way to set up this problem that's a little more straightforward and tends to avoid any errors with sign. We'll look at that later. But let us now talk about some limiting cases for the acceleration of this Atwood machine. What if mass B is way greater than mass A? For instance, if mass B is 1,000,000 and mass A is 1. I'll draw a silly picture here. That would be like a paper clip for mass A and one of those Acme dumbbells in the Looney Tunes cartoons. What would you expect this system to do? Is this paperclip heavy enough to get this to move? Well, of course not. If anything, wouldn't this, I've actually complicated this problem by drawing the floor here. Forget about the floor. I probably should have switched these, but okay, there's no floor here. If this thing was free to move, wouldn't this thing immediately begin to accelerate downwards and the paperclip would begin to accelerate upwards? So at the very least, we know that the letter A, in this case, would be a positive number. We expect this paperclip to accelerate upwards. And the question remains, how quickly will it accelerate? What is the rate at which it will accelerate? So if there's no floor here, can this paperclip really impede the free fall motion of this anvil at all? I would say no. I would expect this to be practically in free fall. There should be almost no tension here. Remember, free fall, the requirement for free fall is that the only force acting on your object is gravity. Now, for this object, mass B, there are two forces. There's gravity pulling down, but there's also a little bit of tension pulling up. How do we know that there's tension? Well, this paperclip's not going to accelerate upwards on its own. If there were no tension, this thing would just fall down at 9.8 meters per second. So there must be some tension to get this thing to fly upwards. But how much tension really is necessary to make this tiny little paperclip accelerate upwards? Not very much. And as you let the mass of the paperclip go to 0, you would need practically 0 tension to get this paperclip to accelerate upwards. So if we look at the formula here, I'm just going to stick with those easy numbers, 1,000,000 and 1. 1,000,000 minus 1 over 1 plus 1,000,000. All right, if this was a calculus class, we could do some more precise things with limits, but isn't this numerator basically 1,000,000? I mean, it's 999,999 divided by 1,000,001. That's really, really close to what number? The number 1. So 1 times g, this is approximately just g. That tells us that the acceleration of mass A in the y direction, well, that's what we called A. That would just be positive g. And the acceleration of mass B in the y direction was negative A, in other words, negative g. Just what we would expect. It should be in free fall, practically free fall downwards. Okay, you could switch these two. You can now imagine that the Acme anvil is up here, the paperclip's down here, and of course you're going to find that this mass would now have an acceleration of negative g. It would be the one practically in free fall, and this one would have an acceleration of positive g. So that's really no different. The last limiting case we could look at, what happens if the two masses are equal? Now, it doesn't really matter if one starts out lower than the other. That's irrelevant. If these masses really are the same, well, can we reason through this? Do we even need the equation? If this thing's just hanging there, wouldn't the tension here equal its weight? And that means the tension over here is equal to the weight of mass A. But if mass B equals mass A, then the weight of mass B is the same as the weight of mass A. In other words, these forces would also cancel, and we would expect them both to just stay in equilibrium. You can make a similar argument even if they're already moving. Like if you gave this one a push downwards and this one a push upwards, they would continue to move at constant speed. They might be moving, but they would not accelerate. And that's what the equation tells us here. If the masses are equal, then the numerator is 0. The acceleration would be 0. So it's important to, when you can, take a look at the formula that plops out of the work you do in a problem and see if it gives reasonable results. Look to see if the results are consistent with your intuition. If you were dealing with two masses of, I don't know, 10 pounds and 12 pounds, and you calculated an acceleration of 5,000 Gs, there should be a voice in your head telling you, that seems a little large. Maybe I should go back and look at my numbers again. I think a general rule is you would not expect an acceleration to be greater than G if the only force in your problem is like the tension in a rope and gravity. You know, if you've got a rocket engine in your problem or somebody pushing on something, fine, that's different, or something slamming into the ground. But in this case, gravity is the one doing the moving. We wouldn't expect to have an acceleration greater than G. Something interesting to recognize about this formula, what if I relabeled things? So I don't have to draw another one. What if I call this MS for standard mass, and this is MX for some unknown mass? Sorry, I should have labeled it here. I know, this is a low budget video. Don't hate. I'd have to rewrite this acceleration equals, this was mass B, so this is standard mass minus unknown mass over standard mass plus unknown mass. And I will attempt to solve this equation for the unknown mass. Let's see. If I move some stuff around, this is what I get. That's an S right here. And I'm going to collect, on one side, I will collect all the terms that have an MS. On the other side, I will collect all the terms that have an MX. And I get MS times, let's see here, A minus G. Okay. And over here, I've got a negative MX times A plus G. Okay. I seem to have run out of space. I'm going to cheat and write the result up here. If I solve this for MX, I'd have to divide on both sides by this. And I would find MX is equal to G minus A over G plus A times MS. The point here is, what if one of your masses, the mass that I'm calling MS for standard mass, what if it was a mass that you bought from Pasco, for instance, and you had a really precise value for that mass, like the manufacturer told you it was 1.00000 kilograms, like you knew it to the nearest hundredth of a gram. If you could then set this Atwood machine up, allow it to accelerate, you've got this unknown second mass on your Atwood machine. So you know this mass really, really well. You'd like to know the mass of this. If you could measure that acceleration very precisely, for instance, by recording it, putting the video into tracker, getting the slope of the velocity, or using kinematics, measure the acceleration as precisely as possible, plug in the known value of G, the known value of the standard mass, you could then solve for the unknown mass. In other words, this is a method for weighing something. You don't have to use a scale to weigh something or determine its mass. Remember, F equals ma tells us that mass is force over acceleration. So push on something with a known force and observe its resulting acceleration. The slower it accelerates for a known force, the more massive that object is. The greater the acceleration for a known force. I'm confusing myself here. Anyway, that's the idea that we're using here. We are applying a force indirectly by tying a string around it, wrapping the string around a pulley, and then attaching some other mass. This is just one simple setup for using F equals ma to weigh something. Towards the end of the semester, we'll look at another way of determining something's mass. You could just put a mass on a spring, pull the spring down, let it go, and this thing's going to bounce up and down. And you can imagine that the more massive this is, the slower it will bounce back and forth. And the less massive it is, the quicker it'll go boing, 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 boing. Again, it's the same idea because the spring is applying a force, and this thing, as a result, will slow down, stop, turn around. It will accelerate. Its velocity will change. So if you want to determine something's mass, apply a force to it and observe the resulting acceleration. In a moment, I'll present a couple other related Atwood type problems, Atwood machine type problems. But you want to understand every aspect of this simple problem because it's got all the essential ingredients for much of the stuff in the following chapters. You've got to write a system of 2 equations in 2 unknowns, arguably 3 equations and 3 unknowns when you start out and not knowing that the equations are equal. So it's a system of equations you have to write. You get those equations by applying Newton's second law and this idea of an acceleration constraint. Then you have to actually do the mechanics of solving the equations and observing sign conventions and all that. So if you can do this problem inside out, it may be simple, but you're better prepared to do more challenging problems where the basic idea is the same. Let's throw a little twist into the Atwood machine problem. How's about, instead of the string being vertical on both sides of the pulley, what if it's something like this? We've got a ramp, which I will pretend for now is frictionless. Let's not worry about friction between the ramp and this block here. We'll call this mass A, and I'll put a little pulley at the end of the ramp here. Around the pulley is a string, a massless string. And for now, just assume that any pulleys we're looking at are massless as well, massless and frictionless. We're going to see that if this pulley did have mass, it would require a torque to get it to spin. And that would mean that the tension here would need to be a little bit greater than the tension here. You can imagine that for a real pulley, if the pull here was the same as the pull here, you wouldn't actually make this thing spin. Okay, this is hardly any different from the previous problem. If you just get rid of the ramp and allow these strings to be vertical, that is the Atwood machine. Let's bring the same procedure to bear on this problem. The acceleration constraint is no different from what it was before. If this string cannot stretch, then these 2 masses always have to move together. That means their speed is always the same, and that means the magnitude of their acceleration is also the same. And you know what? For this problem, I'm sorry, frictionless has 2 S's. For this problem, let's use that alternative method that I mentioned for setting up the problem. Here's my advice. Look at each mass individually. Whichever direction you expect that mass to accelerate, go ahead and call that the positive direction. So I won't even bother writing this down because the results of the problem don't depend on it. But for now, I'm going to pretend that this thing is really heavy. And this one's not particularly heavy, so that we know this one's going to be pulled up the ramp and this one will be pulled, will fall downwards. If this thing was heavy enough, if this was 100 times as massive as this, perhaps the opposite would happen. This thing would accelerate down the ramp. So for now, I'll just pretend that this is the heavy guy, much heavier than this one. And I'll put little arrows. I could even, put an A. I expect this to accelerate that way. I expect this to accelerate that way. And now I'm not gonna mess with any one coordinate system. Before I wrote, positive y, positive x. Let's not do that. I'm going to apply F equals ma along this axis for mass A and along this axis for mass B. And because I expect this one to accelerate that way, I will call this the positive direction. Because I expect mass B to accelerate downward, I will call this the positive direction for mass B. If you use this method of setting up the problem, you have the least likelihood, I would say, of making sign errors. So that's what I'll stick with for now. Mass A, let me draw a free body diagram. We have tension pulling up the ramp, that's T. We've got gravity pulling down. This is mass A times G. And I should have labeled this angle theta. And let's decide what's given in this problem. Well, much like before, let's suppose that we're given the masses. And in this case, we also know theta. And we'd like to find the acceleration. Incidentally, in the previous problem, we could have gone back and solved for the tension if we wanted. If I can find a word here. Yeah, we found a formula for the acceleration. If you plugged in the masses, you could have gotten an actual number for A, which means you could then get a number for the tension. We can look at that another time. Okay, well, since I'm going to write F equals ma along this axis, I need to resolve my gravity force into components, one of which is along this axis. So as you've hopefully done many times already, make a right triangle out of your gravity vector where the original vector is the hypotenuse. And hopefully you're aware that this is also theta. So the component I'm interested in is mg sine theta, and observe that if up the ramp is positive, this force is going to have a minus sign in front of it. So, I could say F equals ma. If I wanted to put a subscript, perhaps I could call this the x-axis. But you know what? How about I just skip over that and say T minus mg sine theta, specifically that's mass A, equals not 0, but mass A times its acceleration. What I've written here is F equals ma. But right now I'm talking about mass A. The m in F equals ma is mass A. So this is the net force on mass A. Now, what about this letter A? If I'm expecting mass A to accelerate upwards, and I'm calling this the positive direction, then A would be a positive number. That's also reflected in the choice here. You can tell from this equation already that I'm calling up the ramp positive, because we know that the tension pulls up the ramp. If I had called down the ramp the positive direction, this would have to say negative T. Because if down is positive, any force in that direction would get a minus sign. All right, but I'm going with the easiest choice. Just like before, we have two unknowns, the acceleration and T. I cannot solve for two unknowns using one equation. It's up to me to find a second equation. Where on earth are we going to go to get that second equation? Let's apply Newton's second law to mass B. I'll draw my little FBD. If mass B is indeed accelerating downwards, then the gravity force on it would have to be greater in magnitude than the tension, which is why I'm drawing that force a little bit longer. And again, I could decide to call this the y-axis so that I can write F sub y equals ma sub y. Let's skip over the details and go straight to gravity minus tension equals mass B times A. And let's think about this carefully. If down is positive, then this force should get the plus sign, which it does, or which it has. And is this consistent? Well, up here we decided that because of my choice of coordinate system, A is a positive number. In this equation, I'm calling down positive. So do I expect mass B to have a positive acceleration? Yes, because I'm assuming that it accelerates downwards. And that checks out. Over here, we've already decided this is a positive number. So mass B would in fact have a positive acceleration. If that's confusing you, I don't blame you. That's the reason for this choice, this convention of check each mass, whichever direction you expect it to accelerate, call that the positive direction. If you stick with that rule, you're less likely to make errors with sign, and you don't even have to worry about it usually. So that's my recommendation. Okay. Once again, we have two equations. I will label these equations 1 and 2. And this method of setting up your coordinate system has the added advantage that very often, once you've written your equations, you've already got a negative T and a positive T, making it easier to do the algebra. The simplest way of solving these two equations for A would be to add them up. That would immediately eliminate the tension. We've got a negative t here and a positive t here. So let's see, how can I write that? I'll say equation 1 plus equation 2. And I won't even bother writing these this time. I know they're going to cancel. When I add these up, they both have a g in common. So I can factor out the g and write mass B minus mass A times sine of theta, all of that times g. And that's got to equal, on the right side, they have a common A. I will factor that out. And we just solve for A. Just like before, it's this coefficient in front of the free fall acceleration. We could plug in any given masses, any given angle, and find the acceleration that we expect. This is something you could do in lab. It wouldn't be difficult to set this up and then use tracker or kinematics to confirm that the experimental acceleration is very similar to this theoretical acceleration. And let's just check something here. Can we recover the original Atwood machine acceleration from this problem? This formula that we arrived at for the regular old Atwood acceleration, can we recover that from this fancier looking formula? Well, what would you have to do to this angle before this setup looked like this setup? I hope you recognize that as theta becomes larger and larger, here's theta already approaching 90. Horrible drawing, but you can see it's starting to look like the original Atwood machine. So if you actually plug in 90 degrees here, sine of 90 is 1, and you recover the formula from the regular old Atwood machine. So it's kind of nice to see that sometimes as a check. Take a more general problem and make some extra restrictions and reduce it to something familiar. Here is yet another variation on the simple Atwood machine problem. It's almost identical to the previous problem, but now let's acknowledge that there's probably going to be some friction between this block and the ramp as the block slides up or down the ramp. And because you've got two surfaces actually sliding past each other, we're talking about kinetic friction, right? Maybe this is a wooden block on a wooden ramp. You could look up that coefficient of friction in your book. I think it's something like 0.2. One of the difficulties is with this problem, or maybe the difficulty, is recognizing that the direction, the friction points, depends on which way this mass is moving. If this mass is sliding up the ramp, then the kinetic friction would have to point down. As a general rule, you can always assume kinetic friction points opposite the velocity of the mass that's experiencing the friction. And if you can't see why, just imagine how weird it would be if the opposite were true. What if you hit the brakes on your car and the wheels locked and you heard that squealing and the friction actually made your car go faster? I mean, wouldn't you want to harness that and like not have to use any gasoline? You could just keep going faster and faster because of friction. The universe wouldn't make any sense if it was any other way. So if the block is moving up the ramp, friction points down. If the block A was sliding down the ramp, kinetic friction on block A would have to point up the ramp. And of course, we get the acceleration by writing F equals ma, by using our free body diagram. If you switch the direction of friction, you're going to change the resulting acceleration. So we kind of have to decide before writing our equations which direction this block is moving, up or down. So in a problem like this, that would have to be stated. How about we assume that mass A is sliding up the ramp. And with that definite choice, we know that the friction on mass A will point down. Now, this is a subtle point. Just because mass A is moving upwards doesn't necessarily mean that mass B is the heavy one. It could be that mass A is so heavy that if the system started from rest and you just let let the system go, mass A would start to slide down spontaneously on its own and drag mass B upwards. But what if, despite the fact that mass A was much more massive, what if you had given it a push up the ramp? So it's going to move up the ramp, but it will be slowing down. On its way up the ramp, gravity would pull down on it, and so would the friction. And it might come to a stop and then start to slide back down the ramp. But on the way back down, gravity would point down the ramp, but the friction would now point up. You might expect that the acceleration will be different in those two cases. So the number that you get for the acceleration would change depending on whether mass A is sliding up or down. Okay, but we have this definite choice. Mass A slides up the ramp. Let's look at the free body diagram for mass A. So this is getting successively more complicated. This problem actually will require significantly more writing than the previous two. We still have tension parallel to the ramp, but now, because mass A is presumed to be sliding up the ramp, we've got a friction force backwards. I'll call that F sub K. Don't forget about gravity. I will go ahead and resolve that immediately into components parallel to and perpendicular to the ramp, this angle theta. And we're not quite done. There's one other force that you should be able to identify. Where does this force come from? Well, that's the ramp pushing on the block, but there's another component of the ramp's contact force with the block. In addition to the ramp pushing that way, it's also pushing that way. That's the normal axis. So we call that the normal force. Okay, and I will remind you, you can always, in this class, you can always use this simple model for kinetic friction. We always just assume that it's proportional to the normal force, and that constant of proportionality is mu sub k, the coefficient of kinetic friction. So if you have twice the normal force, you would expect twice the friction. What is the normal force? You cannot just assume that it's equal to the weight of mass A. That's a common mistake. The only way to know for sure what the normal force is to write F equals ma along the normal axis, because n is going to appear in that equation, and you can solve that equation for n. So I think I'll do that first. And now, because we've got this more complicated setup, I probably do need to label a coordinate system. How about for mass A, I go with this choice. Positive x is up the ramp, positive y is normal to the ramp. And I'll start by saying the sum of the forces in the y direction is mass A times the acceleration of mass A in the y direction. So I'm applying F equals ma along this y-axis and for mass A. Since I've called away from the ramp positive, this gets a plus sign, and the adjacent side of this triangle gets the minus sign. So I say n minus, well, how do we get the adjacent side? Take the hypotenuse, multiply by cosine. mg cos theta. Sorry, that's a little illegible there. And we're going to set that equal to, well, here's where you have to make a choice or use your judgment. Is there any reason that you would expect this mass to be accelerating normally to the ramp? Why would it be flying up off the ramp? I don't see any force in that direction. It doesn't have a rocket engine attached to the bottom. The only force on this thing would be the normal force and the rope. So we expect it to be accelerating purely in this direction. This direction is orthogonal to the y-axis. I expect this acceleration to be 0. And now we immediately have an expression for the normal force. Since we're given mass A and we're given the angle of the ramp, we can plug those numbers in and get a value for the normal force in newtons. Let's save that for later. You can probably see we're going to need that in the next equation in order to find the friction force. Okay, so I'm still talking about mass A here, but now I'll say that the sum of the forces in the x direction is mass A times acceleration of mass A along the x-axis, or the x-axis for mass A. Go back to the free body diagram. Since I'm calling up the ramp, the positive direction, T gets the plus sign, F sub K gets the minus sign. T minus F sub K. Have I missed anything? Aha, don't forget, there's also a component of gravity down the ramp. You have to work against gravity as well. So you have to make sure you've included all the forces you can think of in your free body diagram so that those forces show up in your equation. Minus mg sine theta, that's got to equal, okay, well this time I'm not going to write 0 because the acceleration is not 0. We expect it to have, in fact, some acceleration parallel to the ramp. Now, I'm going to use the same rule that I used in the previous problem. Let's just pretend that this one's really massive, it will fall downwards, and this will get dragged up the ramp, or that it's got an acceleration up the ramp. If I just assume that the acceleration is up, I will call that the positive direction. I've already done that, really. And let's just call the acceleration A. If the string cannot stretch, mass A and mass B must have the same magnitude of acceleration. It seems to me I've got 1, 2, 3 unknowns. Right? Kinetic friction is not among the given quantities. However, let's now use this result, this model for kinetic friction. I'll plug that in here. T minus mu times the normal force. Well, I'm going to go ahead and substitute. We've already found the normal force. So you had to do the y equation before you could make the substitution into the x equation. There's a minus sign here. So this is getting a little messy compared to the previous problems. And now only 1, 2 unknowns remain. We're given the coefficient of kinetic friction, we're given the masses, and we're given the angle theta. Okay, I have 2 unknowns in this one equation. I cannot solve for those 2 unknowns with this single equation. I still need another equation. If we wanted, we could count how many unknowns there are. Arguably, you've got 2 unknown accelerations, an unknown tension, that's 3 unknowns, and an unknown friction force. So you could technically say that there are 4 unknowns requiring 4 equations. Well, I've already written 1 equation, 2 equations, 3 equations. I've already written 3 of the 4 required equations, but I don't even like to think about this as a separate equation. I don't like to think about the kinetic friction as a separate unknown. To me, it's just the acceleration and the tension. And that's all equivalent, however you want to think about it. But hopefully you recognize now we need to look at mass B. And the rule that I'm following is whichever direction I expect the thing to accelerate, call that the positive direction. So I suppose I could call this the positive y-axis for mass B. Say some of the forces in the y direction is mass B times the acceleration of mass B in the y direction. Truthfully, even if you had left off these subscripts and just launched right into F equals ma along that axis, that would probably be fine. Which force gets the plus sign? Well, I suppose I should draw the free body diagram. Gravity is down, tension is up. And I went ahead and drew this one longer because I expect this one to be the mass that accelerates downwards. Gravity minus tension equals mb times. And now I'll go ahead and substitute the letter A. Just call the acceleration A if you're going to stick with that rule that I've described. Okay. I'll call this equation 1. You can barely tell that that's a number 1. Sorry about that. This is equation 2. We have 2 unknowns in these 2 equations. We don't know the tension, we don't know A, but we're being asked to find the acceleration. You could be asked to find the tension. The quickest way to eliminate T, just like before, would be to add the equations. I'll do that on another sheet of paper here. There's something so satisfying about the sound of rifling through pages. if I add equations 1 and 2, the t's will go away. This term added to all these, what do you notice in common for all three of these terms on the left sides of the equations? They seem to all have a g in common. So I will factor out the g, and I get this, mb minus, I could even go further and also factor out an ma here. Let me do that actually, minus ma times, I would have a mu cos theta plus sine theta. And if you're not following all my steps here, I've done a couple factorings all at once because I've seen this stuff so many times. You should check my results here. But when you redistribute everything in here, you will recover this term, and this term. You don't have to factor it in the same way that I did, but I did this because it's a little easier to look at. Got all the angular stuff isolated. On the right side, this term has an A and this term has an A. So this one's pretty easy. On the right side, I would factor out A, and I just get the sum of the masses. Okay, the last step would be to solve for A. Just divide both sides by the sum of the masses. And we get something that, once again, looks familiar. Oops. MB minus MA UK cos plus sine. And instead of writing brackets, I'll just put the G off to the side of the fraction. There it is. Okay, fine, I'll put the brackets. Not a formula worth memorizing. I don't have this memorized. I hope you don't take up valuable storage space in your brain to memorize this formula, but I suppose you could. It's much more important to know how to draw your free body diagrams, write your formulas. Can we recover the original Atwood machine formula from this formula? Actually, before doing that, can we recover the formula from the previous problem? In other words, the same diagram, but just get rid of friction. Well, if there were no friction, wouldn't that correspond to a coefficient of friction equal to 0? A frictionless ramp would have mu sub k equal to 0. And that means this term would be gone, and you would just be left with minus ma times sine theta. And that's, of course, what we had previously. Can I find that? I need to work on my organizational skills here. Yeah, there's that formula. So we're just adding successive layers of complication here, but none of it's really that bad. It's the same procedure every single time. Identify your masses. For each mass, draw a free body diagram. Convert your free body diagrams into equations using F equals ma. And at that point, it's just an algebra problem. So the least interesting part would be plugging in actual numbers. That part's easy. You do want to get some practice with that with your calculator. Here's one reason, one very important reason you want to get practice with that, because since we're no longer meeting in person, I'm probably going to have to give multiple choice exams. And that means partial credit is irrelevant. You have to get the right number. Maybe there's a way around that, but I just don't see how, because I can't expect everybody to have access to a scanner. I think I'm going to have to use multiple choice exams. That's good and bad for you. It means simpler problems, but it also means the stakes are higher for each particular problem. No partial credit. You got to get the right answer. Okay. I'll make one other remark here. What if these numbers were such that this quantity had a greater absolute value than this quantity? In other words, if the numerator came out negative, A would be a negative number. I'm using A for the acceleration of mass A up the ramp. I was assuming that mass A would accelerate up the ramp. But if we plug in all the numbers and A comes out negative, that's fine. What it tells us is that the acceleration is actually directed down the ramp. So if my positive axis points up the ramp, but A comes out as a negative number, that would mean that the acceleration was down the ramp. It doesn't change the assumption that mass A is moving up the ramp. So the velocity is still up the ramp, but the acceleration is down the ramp. What's the rule? If V and A point opposite, what is your object doing? It's slowing down. So the situation would be, yes, mass A is moving up the ramp, but it's slowly coming to a stop, or not necessarily slowly, but it's slowing down. At some point it would stop. Perhaps it would then slide down the ramp. If it slides down the ramp, the friction would point up the ramp. And that means that your free body diagram would change, your equations would change, and the numerical value of your acceleration would also change. So this answer would only be applicable for while the block is moving up the ramp. I think that's enough Atwood machine garbage for now. After this, I will choose problems from your chapter 7 homework and work some of those. And we still need to talk about drag. I'll have to go back to your chapter 6 homework and look at 1 or 2 of the drag homework problems and talk about our quadratic model for drag.